In our last lesson, we discussed several concepts involving integrals, including net change and average value. In today's lesson, we're going to apply those concepts to particle motion. So let's review one more time the net change concept, which allows us to go from a derivative f prime backwards to an original function f. So in formula form, we are actually using the fundamental theorem of calculus part 1. So we integrate the f prime, which is a rate of change or derivative, and that's equal to f of b minus f of a. And the resulting units will be the same as the function f of x. We're able to use that relationship in two different ways because we know that acceleration and velocity are both rates of change. So if I were to go backwards from acceleration, that would lead me to velocity. So integrating acceleration gives me the change in velocity over time. So to evaluate that, we would do v of b minus v of a, and we would get the same units as v of t, which we learned in the first half of calculus that velocity always has units of distance over time. To find the change in position, we'd have to go backwards from velocity. So we would do the integral expression of velocity over time, and that would give us change in position. You need to know that's also sometimes referred to as displacement. So if you see that in a question, it is talking about change in position. And to evaluate that, we get x of b minus x of a, and those give us the same units as the position function x of t, which is just distance. It's not divided by time because it's not a derivative. In both of these situations, your v of b and your x of b might be referred to as final values, while your v of a and x of a will be referred to as initial values. So just a little more terminology to be aware of. The next concept is total distance, and before we talk about how to evaluate that, I want to compare it to displacement because those are two concepts that are easily confused. So I have this little drawing or sketch next to us that shows the difference between the two concepts. So if I were to go from point A to B and I took kind of a long bumpy path, the total distance would be how far I actually walked. The displacement, on the other hand, would be what is the difference between my starting point and my ending point. So I hope that little picture shows you the difference between those two concepts. The first thing you'll probably notice about the expression for total distance is the integral is the absolute value of our velocity function. And the reason we need that absolute value is because that total distance sums up all positive and negative velocity values. So another thing you need to know is that the absolute value of velocity is the speed. So it doesn't take into consideration which direction you have traveled. It just adds up all of that distance. So the units resulting would be the same as your position function, so it's just a measure of distance traveled. The last two concepts on our chart are both applications of that average value concept that we learned in our last lesson, which is the 1 over b minus a times the integral of the function. So to find the average velocity, we apply that formula to the velocity function, and it results in the same units as velocity, distance over time. It works the same way for acceleration. So to find the average value of acceleration, we use that formula for acceleration, and it gives us the units of acceleration as well, so distance over time squared. Let's take a look at an example and try to apply some of these concepts. So we're given that a particle starts at position x of 0 equals 14, so in other words, that's our initial position, moves along the x-axis with velocity v of t, that's 8 minus 2t meters per second on the interval 0 to 6. The first thing we're asked to do is to graph the velocity on 0 to 6. So I made a quick chart of t and v of t values, knowing that my x-intercept would happen at 4. I didn't go and do all the values from 0 to 6, but just enough to get a good sketch of our graph. The first thing that we're asked to find is the final position at t equals 6. And knowing that I'm given velocity, to get any kind of position value, I'm going to have to go backwards on that particle motion PVA hierarchy. So that leads me to believe that we need to start with an integral of velocity from 0 to 6. So after setting up that integral, I realized that the right side of that equation is the rest of the fundamental theorem, which is x of b minus x of a. And since we have already sketched a graph of this velocity function, we'll go ahead and use area to evaluate the left side of this equation. We have two triangles in that graph. The first is above the x-axis. It's a little bit larger with dimensions of 8 and 4. And then the other smaller triangle is below the x-axis, so we'll subtract that. And the only thing I was able to do on the right side of the equation is to substitute in my initial position, which is given to us as 14. So simplifying the area and then adding over that 14 to both sides gives us a final answer of 26 meters, because that is the position at time 6. The next thing we're asked for is displacement, which, believe it or not, we actually found in the last question through the process of finding the final position. And that is because the displacement is represented by the left side of that equation. So if you knew that, once you calculated the area, you would know your displacement is 12. But I'd like to show you another way, just in case you forget that you've already found the displacement. So another way to think about displacement, it is the change in position. And anytime you want to change, you just take your final value and subtract your initial value. So we found that the final position was 26. Our initial was given at 14. So when you find the difference between those, it's 12 meters, which again was already found by just evaluating that area of the integral. The total distance formula is almost identical to the displacement, except for the one special difference of those absolute value bars. So in terms of our area that we use to evaluate the integral of v of t, absolute value means that all of that area becomes positive. So we'll take that smaller triangle and flip it up over the x-axis to make it positive. So instead of subtracting here, we'll actually add it to get our final answer. When we do those calculations, we end up getting 20 meters, and meters again because it's a distance. We'll do this last example with a function instead of a graph, just to show you how to evaluate that differently. I'm given initial velocity and the function for acceleration on 0 to 3, and asked first for final velocity, so I know I'll have to go backwards from my acceleration function to get there. So I set up my fundamental theorem part 1 formula and went ahead and replaced a of t with 6t squared equals v of 3 minus v of 0. And since we're using a function instead of a graph this time, we'll have to find the antiderivative of 6t squared, which is 2t cubed. We'll evaluate that from 3 to 0, and I went ahead and also plugged in my v of 0 is 9. When I plugged 3 into the antiderivative, it gave me 54, 0 gave me 0, added the 9 over, and so 63 feet per minute would be our final velocity at 3. When you're asked about change in velocity, it's like the last example. You might realize you've already found that value by doing the process for final velocity. It is 54, but the alternate way to think about it is the change is the final minus the initial. So the final we found was 63, take away that initial 9, and again 54 feet per minute is the change in velocity. The last question about average acceleration is going to allow us to practice our average value formula again. So applying it to acceleration, we have 1 over 3 minus 0 times the integral 0 to 3 of our acceleration. So I realized that we've already evaluated this integral from 0 to 3 and came up with 54. So that just gives me 1/3 of 54, which is 18. And since it's the average acceleration, we need units of feet per minute squared. So since we just did an average value example, I wanted to point out that a major confusion is between the two average formulas. We have average value and average rate of change. The average value finds the average of the given function. So for example, if you were given velocity and asked for the average velocity, that's the formula you would use. On the other hand, average rate of change actually finds the derivative of the given function. So in that case, if you were given position, but then asked for the average velocity, that would need a derivative, so you'd have to use the average rate of change formula. So it's really important to know the difference between those two formulas and also when to use each of them. So we'll talk about that some more as we start the examples in class.